So, hello at Conf42 Site Reliability Engineering 2025. Glad that you're here and listening to my talk. Yeah, let's buckle up and deep dive into it. The session title is Real-Time Earthquake Alert System, leveraging serverless architecture with Confluent Kafka. Basically, it's a project which is mostly built in AWS cloud with specific services, mostly serverless, and also in a combination with Confluent Kafka just for the message distribution and achieving a fast kind of delivery of the notifications. Who am I? Some bold lines about what I'm doing or what I did in the past. Cloud development, cybersecurity, all kind of projects, architectures, designs, consultancy, everything like this. Projects in data science domain, from data extraction, data modeling, until, let's say, a full ATL pipeline or anything like that. So just trying to provide from real scenario data something that's practical. So just having practical projects based on specific demands of data. Multiple security research is for top Romanian banks. So yeah, also this one is very interesting. So let's say pen test, if you want to call it like that. And AWS community builder in serverless niche for 1 year right now. If you have any questions after this talk, ideas, remarks, anything like that, you could contact me on mail or on LinkedIn. These are my addresses. So yeah, enough about me. Let's try to explain what's in this project. The story behind the research project is like spread it between these questions. So these bullet points, let's say questions. For example, the first one, why the need for high performance earthquake notification system? I'll start by providing you an interesting story of what we currently have in Romania in terms of Romanian alerting system, which is provided by the government. It's the Romanian Alert application, which reaches like very low hardware in our telephones. So it's basically delivered with the telephone. And they are just emitting these kind of alerts for bad weather, critical accidents, critical infrastructure failures, anything like that. But an interesting point here is that in very large of the cases of notifications, we receive those alerts after the event unfolded. For example, after the bad weather was just gone. So if you are seeing the rainbow, you will just receive a message. So that's not very good. Although the project and what the government develops is very good. Very nice ideas. This is why I was thinking back then, 1 year and a half ago, why not having also a kind of notification for earthquakes? In that time, I was thinking to just have the notifications when the event is happening, because I was thinking that I cannot predict. So I cannot have the machine learning model which is just trained on previous data and just will predict something, because it's so critical and it's, let's say, unpredictable. Let's say it's a natural happening. So I started to look around and see what kind of data could I use, because I cannot just put in the ground some systems and just have some data from those, at least not right now, because in what I'm about to tell you is where I found basically that the data and in which project. I found that there is an institute of seismic movements and earthquake researches linked to the Romanian government, which has some very talented researchers and very interesting projects there. And in those projects, there was a kind of a very interesting one called Rapid Alerting System or something like that, which was based on some physical systems placed in west of Romania, in the, let's say, the well-known area of seismic movements, at least in the couple of years. So they placed those systems in those areas and they are just emitting data when the very little seismic movement is detected. So until now, very interesting thing. But I was also thinking, okay, so that town is like in distance, like 500 kilometers from Bucharest, which is the capital of Romania. So if we are translating like the kilometers in some time thing, there are some couple of minutes until the full waves, for example, like a 7 earthquake hits. There are like a couple of minutes, or at least 1-2 minutes until the full waves are received in Bucharest. In our towns, like in the north, central north, 3 minutes, 2-3 minutes, something like that. So I was thinking, why not having this advantage? So having the advantage of time, distance and time, use those systems, basically that data, which is exposed by them in a browser application, I think right now. And I can just listen to that data and use it to spread it to certain consumers, basically, and subscribers, which can be people or critical infrastructure things. So I just responded almost to also the second question, where to find good real-time earthquake data. So like I've said, this institute provides very interesting projects, and that particular one with the systems placed in the ground emitting data at the very little seismic movements, it was very helpful. So we integrated with that emitting system, and we are listening for events basically. Why choosing the serverless ecosystem? So I'm ambassador in AWS for serverless, lambdas, and anything related to that. It's from my perspective, due to my previous projects, I integrated lambdas, serverless, like anywhere. But beside the knowledge, it was also practical. Why I'm saying practical is because for this particular project, we don't need non-stop servers like 24/7. We just need some listeners which need to be prepared when the earthquake hits, just to spin up those kind of instances, containers, and use them to just spread and distribute very fast the notifications. This was the first thing. The second thing is also the costs, because if we have like servers up 24/7, it's also a matter of costs to be involved and how to scale them just on the fly, like in milliseconds. So these two things were the base pillars of choosing AWS, lambdas, serverless. Moving on to the architecture of the serverless notification system, what you see here is the base architecture, which is the first version, let's say. I'll try to explain you like in big lines, because we will deep dive in the next slides. What in the gray is like the backbone of the system, which has the lambda producers, which I'm calling like lambda producers because of the Kafka integration, and also the Lambda consumers in the right, and in the center you have the topics, partitions, the backbone of Kafka itself. The yellow ones are like the error handling mechanisms, SQS, dead letter queues, just for putting all kind of errors, like if there are errors, networking or latency or things like that, we'll just retry on that code execution. But if it's like a major failure, we'll just put it in a particular queue and keep it there for manual studying of the logs and of the error itself. The blue ones are for monitoring, just monitoring the number of instances, how the system behaves. Costs, again, are very important because I will show you afterwards, we are also scaling up. So we need to see the costs and how the system behaves, like with a, let's say, central kind of monitoring for everything, for errors, and yeah. Also the end channels, if you view them, you can view them in the right. You like SMS, mail through AWS, SES, or through Telegram, which is like a backup thing from our end, from our perspective. The purple ones are for CI/CD, like pipelines for creating the infrastructure, but also we are thinking, you can view it in the next slides, to scale up and down through this kind of CI/CD idea. The build, some scannings, just automation things on the repository, and the block with green, it's like the application, the web application, where the end subscribers or the critical infrastructure members could join into the backbone system. What I'm trying to say, join, is like just subscribe in the system, provide maybe a telephone number or some kind of informations about the subscriber, and based on them you can see there that there is a database, that's a Dynamo database connected to the backbone of the system, which will be just iterated. So we will just iterate through the members, through the subscribers, and try to notify everyone. Also some Lambda functions there for the different kind of APIs, some protections through the firewall. The main application was, we're thinking to put it in like a Kubernetes infrastructure, but we will see, maybe use a kind of serverless also for that one. Architecture of the base notification system, like I've said in the previous slide, this is the backbone, the gray area, if you call it like this. You can see the Kafka producers, Kafka consumers, and the Kafka topics in the middle. In the Kafka producers, we have this thing called multi-threading, just using the, let's say, full capacity, full resources of instances of Lambda, the CPU, so just using the full capacity, and try to separate, let's say, threads and link them to certain partitions or topics in Kafka. So this is the beginning of rapid or fast production notification, basically the first step. We are trying to put like also a topic roulette on top of what Kafka has, like for topics partitions, and try to not overwrite messages in the same partition, same topics. Just try to have a thread and a partition and put the message on that, and try to connect it to the Kafka consumers. This is also like an interesting key idea of this project, to have the partitions and basically the topics in Kafka triggering certain instances of Kafka called consumers. Achieve a parallelism, distributing the message the most fast way possible can be. The yellow box is monitoring, and monitoring at least for the kind of major failures. So for the errors, which are put in like the error queue, and for the failed events just networking, latency, things like that, we'll try to retry 2 times, 3 times. We have the end channels where the notification is sent, SMS, mail, Telegram is backup, and the Dynamo. So the database, the blue one, is where the subscribers are just present, registered. Yeah, and the Kafka producers listen for that data which I've explained before, which is provided through the systems of the institute. Another interesting thing here, we'll deep dive a bit into the architecture of Kafka integration in the serverless context. Like I said, Kafka is here to somehow parallel distribute the messages, the notifications, and to also trigger parallel pins of Lambda consumers. So every partition will have a certain code execution, like a certain trigger, let's say, certain Lambda as a consumer, which will try to notify a certain subscriber. We have the threads, just using the resources, the topic roulette built on top of what Kafka already have for topics partitions, and try to fill up every partition to be able to trigger from it the Lambda consumers, which have the logic to just iterate the database of subscribers and notify them in the end. Yeah, so here we also have some yellow dots, which represent like the scaling possibilities. So scaling in terms of resources, threads, and the scaling in terms of partitions, topics, and in the Kafka consumers, just trying to scale the triggers based on what Kafka has, and also the Lambda consumers. The Lambda Kafka producers key elements, we have the multi-threading, explained in the previous slide, using those resources from the Lambda instances, thread lock to not write in the same topics from separate threads, using partition number to not overwrite data in partitions, and using Lambda retry and SQS dead letter for major failures. And the retry is just for latency, networking, minor problems. The Lambda Kafka consumer key elements. Here are some nice ideas from our perspective. Custom timestamp lock for mechanism for parallel Dynamo update. So we are trying to, here was an interesting dilemma, let's say, because we saw that there were multiple notifications for a certain subscriber. So let's say one man, one fellow could receive multiple notifications, and the second guy could not receive anything, just because there was a race between them, and the first one won and just had all the notifications there. So we wanted to just lock somehow certain subscribers if those were notified. So basically the code already was applied on them and they received, or it's like in progress of receiving a notification, and not trying to notify it again, just moving to the next one. This is like the lock per subscriber, so per item, to have for each individual one notification. Optimistic locking in the custom Dynamo concurrency control is a method just built on top of the first one with the custom timestamp lock. We're just putting like a version, and we know if the version changed, if we need to notify the subscriber or not. Just, let's say, another fence of achieving the concurrency and the fast thing, but also to notify all the subscribers and not miss one of them. Yeah. Using Lambda retry and SQS dead for errors like for the Lambda producers and Lambda consumers using a cold start, warm start methodology. We are seeing that using a warm start helps because it's the last phase of the notification. So started from the producer, reaching the Kafka cluster, and after that we need something that's in a ready state. Just have it in there, a number of instances and lambdas, and try to have them in a ready state, just ready to go to the list of subscribers, execute the code for each, and send in notifications. But this is again an interesting procedure also in auto scaling, basically. So if you have like thousands of subscribers or reaching a certain number of subscribers, maybe you need certain instances in warm state, the rest in cold start, things like that. The Lambda Kafka consumer integration with database. So there is like a custom dynamo locking. This was the first version, like I've explained a bit in the previous slide. So from the earthquake topic, the partition, we're just trying to trigger a certain Lambda execution. And from that execution, the code will act on certain items. And using this kind of lock, like the timestamp on which we are placing the lock, we know that an item is in progress of being updated or it was just updated, like 1 millisecond ago, something like that. And the next trigger, so the trigger topic 2, will go to the next one. So just going like a domino thing, but from the front. So viewing like a domino row from the front and just going gradually with each trigger, so with which partition, just going through each subscriber and notify each one of them. This is for just using the full capacity of triggers and not wasting like multiple triggers, so multiple code executions on a certain item. Although there is like a loop, so going gradually through the items, we can end up using the same trigger for the same item. Yeah, it won't be notified like twice or 3 times, but we'll have a waste, let's say, of time. So the trigger will act like twice on the same item, but just updating it once. Yeah, this is like the first version of what we were trying to achieve. Concurrency of notifications and also notifying the subscribers in a fast way and notifying all the subscribers. The custom dynamo segmented subscriber processing. This was like the second version of the Lambda consumers logic. So from the previous version, we are trying to segment the list of subscribers and having like locks per certain segments. So for example, one trigger from a partition from Kafka will just act on a certain segment and just lock that segment with a block ID or something like that, from ID 1 to ID 400, something like that. So just the trigger will act on that particular segment. So in this one, the triggers won't conflict. There won't be any race conditions, let's say. Each trigger will be allocated to a certain segment and will just do the work. So the trigger can be viewed like a worker. So the worker will do the job just for that segment. So from now, we can view that domino abstractization from the parallel, from the lateral view. We are viewing with workers, like soldiers, just particular segments of items, which are basically subscribers, people, infrastructure members, things like that. So just on them the workers will focus. This is an improvement in terms of how we are reaching those subscribers through Kafka partitions, topics, and Lambda code, different kind of Lambda code executions, which are done in parallel. Also, moving with this parallel view through the end. So having the triggers, the workers act in parallel, the subscribers. But although having one worker per segment, like 1 to 400 or 4000, is like a lot. Even though there will be like very low level multi-threading in that particular segment, you only have one worker. It's hard work there. This is why the second version, so this is like a parallel distribution and segmentation in Lambda Kafka Consumer, there are like maximum invocations and locks per segment, also like domino style, but we let multiple executions, so multiple code triggers, to just act on, let's say, particular segments. So we allow multiple workers to work on the same segment and doing that low level multi-threading. So letting, I don't know, maybe two, like in this example, we let two triggers just act on the same segment. So they can resolve or notify and execute the code or faster, let's say. We can allocate, like in this example, maximum workers, like 5 or anything like that, just depending on the segmentation, which is done like in an automatic way. Just having the maximum number of subscribers, maybe dividing somehow that list, and having the numbers of locks, maximum workers, things like that. So what's the important idea is that we are viewing the domino from the lateral view, and we have multiple soldiers allocated for the same segment. They will not conflict with each other, there won't be any race conditions between them. They will just act like multiple workers, so dividing the work in the same segment. This is like the improved version of the distribution between the Kafka code execution, the Lambda code execution, and the Dynamo where we store the subscribers. So this is like the level right now, but we are also trying other things and just improve the speed and everything, like I've said, with that granular multi-threading applied at segment level. So it's very low level, I could say. So we will just keep on researching and see what's the best for that moment, increasing every time with new possible ways. Again, one interesting thing. So like I've said, Kafka was integrating here just to resolve this parallel distribution. But instead of Kafka, we could use Kinesis from AWS, which could work well, or a different kind of queues to just be close to the cloud, not go to the internet, the cluster, and just come back. Just be in the same network. Maybe it could decrease the latency, but this is for the later. Some things about autoscaling, which is very interesting for this project, because we don't want to have manual interventions when it reaches like a base kind of stable state, the project. We won't need those manual interventions anymore. This is why we were thinking to put in place a kind of auto scaling, just scaling up or down the system based on the number of subscribers. So if we have like a range between, I don't know, 0 and 201 or 301, we'll just increase with threads, so basically resources allocated in the Lambda producer instances, topics, partitions, the Kafka clusters, and also the number of triggers and number of Lambda consumers. Yeah, like the warm state consumers. If we are going down with the subscribers, we can just lower the resources on the fly. Again, if we, yeah, it's hard to predict something to auto scale through the roof before having that major earthquake, but at least there is a possibility to scale it based on this number of subscribers. For now, this is our idea for now, but we can think about some other features, let's say, which could be linked to auto scaling. Not predicting, because predicting is hard. We need something that's realistic. So this was made through custom scripts, like some Python combined with Azure, with AWS CLI commands for Lambdas, for the Kafka clusters, just on some custom scripts. And these were placed in a Lambda, like an external Lambda, which orchestrates the entire auto scaling and everything. These kind of external Lambdas act also like for the previous segmentation, just allocating different kind of maximum workers, segmentation IDs, just on the fly, again, viewing the number of subscribers, just doing the calculations and having these numbers. The custom auto scaling using Terraform, so infrastructure as a code. So right now we're trying to reduce the custom scripts, so custom shells and things like that, and just move to an infrastructure as a code, something that's more used in every project right now, software project. It's the same kind of logic, just we're also provisioning the infrastructure through infrastructure as a code, so all the services and everything. And we also use it, that's the interesting part, to scale or up or down with GitHub Actions, or we could use something in AWS for code deployment, because we need to check the number of subscribers and to trigger the Terraform execution with a new list of what we need, like parameters, like we need 2 threads, we need 4 threads, we need 4 topics. So these are the kind of numbers which are placed on a certain file, which is sent to Terraform just to execute on that list. So it's a very interesting approach of how infrastructure as a code act for scaling up or down a serverless Lambda AWS architecture and system, basically. Yeah, these were like in the area of development operations, how to operate the entire system when it's like in a stable position, after we figure out the services, what we need, and so on and so forth. This is like a separate lane of how to keep it automatic, let's say. Also for creation of the resources and the services and everything, then to have it a certain time step of them. If something happens, we could revert to a certain step, certain snapshot of the resources and the architecture. And we could also use it for scaling up or down, depending of the number of subscribers in this phase. So this is the project. This is the researches. These are the researches done until now. We are in touch with we have some discussions how to proceed further, how to do other interesting researches for this kind of earthquake notifications, maybe to integrate it in what there is on provided by the governments, not only Romania, who knows, to have it like an alternative on just having some kind of integrations between what's already there, or providing new ideas, anything like that. Yeah, just bringing something to the table, a kind of innovation, we could say. So if you have any questions or remarks or opinions, please feel free to contact me on mail, LinkedIn. Just be aware that the project itself, it's registered. So yeah, if you want to, if you have some inspiration from it, or you want to do something similar, please just contact us or me just in the first place, and we could align and we could discuss firstly. So like I've said, it's a protected project under some licenses. Yeah, we also have some open discussions now and there. So yeah, thank you, and thank you for being here. It was a pleasure, and thanks to the organizers for inviting me to present this research. Thank you.